If you've ever looked at a map of southeast Queensland, you might never guess that beneath those rolling paddocks and granite hills lies the eroded scar of a cataclysm so enormous it rivals Yellowstone and Taupo. It's called the Mungore Caldera, and though few Australians have ever heard of it, it was once the stage for one of the most violent volcanic events our continent has ever known. Today there's no steaming lake or rising dome, no fumaroles or geysers to hint at its fiery past. Instead, the land wears a cloak of quiet. Cattle graze where magma once churned. Farmhouses sit where incandescent clouds once roared. But 220 million years ago in the late Triassic, this peaceful part of Queensland tore itself open in a super eruption that may have not only changed the face of eastern Australia, but the planet itself. But first things first, location. Finding the Mungore Caldera was a tricky little bugger, but I managed to find it after doing some geological sleuthing. Firstly, keep in mind that the land has changed after this caldera erupted. The Mungore Caldera was sliced by the perilineament, which offset its eastern third about 8 kilometres northward. This has warped the once circular shape of the caldera. Thankfully, geophysical tools can be used to help picture the size and scope of this massive structure. When viewed under gravity, we can see two circular shapes. Remember how it's been offset by 8 kilometres on its eastern side? That's this region here. Before it was warped by subsequent tectonic events, it would have fit snug to its western portion. Another thing we see are ring faults, radial structures created by the caldera collapse. But what allowed me to really zero in on its location is this layer, which represents a granite called the Mungore granite. The alteration that occurred to the land not only distorted the shape of the original supervolcanic caldera, but it also created pathways for mineral-rich fluids that still define much of the gold-copper exploration belt there today. To understand how Mungore came to be, we need to step back in time, before the dinosaurs we know from Jurassic Park even existed. In the late Triassic, around 221 million years ago, Australia was still welded to Antarctica and other fragments of the supercontinent Gondwana. The eastern edge of the landmass, what geologists call the New England Fold Belt, was a restless place, a patchwork of island arcs, oceanic crust, and continental fragments that had been colliding and welding together for hundreds of millions of years. For much of the Paleozoic era, this part of Australia was a subduction zone, a bit like modern-day Chile or Japan. An oceanic plate was diving beneath the edge of Gondwana, melting as it sank and feeding long chains of volcanoes along the margin. Those arcs built up mountain belts, and each collision and accretion event left its mark in the form of folded rocks, thrust folds, and granitic intrusions. By the late Triassic though, something began to change. The once compressed margin started to relax, the grinding subduction slowed, the mountains began to spread, and the crust started to stretch. It was the first sign of a transition from a compressional plate boundary, where plates collide, to an extensional one, where they pull apart. That shift would eventually lead tens of millions of years later to the opening of the Tasman Sea and the birth of modern eastern Australia. When continental crust stretches, it doesn't do so quietly. Deep beneath the surface, the hot mantle starts to well up, and new batches of magma intrude into the crust. Some of these magmas stall and cool to form granites. Others, buoyed by gas and heat, push toward the surface, melting and mixing with the surrounding rocks as they go. The result is an enormous unstable reservoir of silicic magma, the kind rich in silica, capable of feeding catastrophic eruptions. That's exactly what was brewing beneath what is now the Mungore region of Queensland. The first signs of the Mungore system were relatively gentle. Rhyolite domes oozed up through the surface, solidifying into glassy lava mounds. These were the heralds of something much bigger to come, the early vents that marked where the crust was beginning to yield. Beneath them, a huge magma chamber, perhaps 10 or 15 kilometres across and several kilometres deep, was assembling. It wasn't a single, tidy body of molten rock, but a mush of crystals, melt, and gases. A simmering stew connected to deeper basaltic intrusions that kept it hot and buoyant. The magma itself was rhyolitic, a sticky, silica-rich composition produced by melting and remelting of andesitic crust with a pinch of basaltic input from the mantle. Pressure built for perhaps tens of thousands of years. The chamber ballooned, and cracks propagated upward. When the roof finally gave way, it wasn't a single vent that opened, but an entire region that failed catastrophically. Imagine standing anywhere within 100 kilometres of the caldera when the eruption began. The ground would have convulsed as magma punched its way through, blasting apart the overlying rock. Columns of ash and pumice would have climbed tens of kilometres into the stratosphere, spreading out like giant mushroom clouds. Lightning would have laced through the darkness, igniting fires in the forests below. The size of the caldera alone is 50 kilometres by 35 kilometres, and it tells us we're dealing with something on the order of 1,000 to 2,000 cubic kilometres of eruptive material. That's the range of VEI8 events, the largest eruptions known in Earth's history. For comparison, Yellowstone's last super eruption released about 1,000 cubic kilometres, and the Taupo eruption in New Zealand about 1,170 cubic kilometres. Mungore's eruption either matched or exceeded them. Ash clouds would have blanketed the sky across the Triassic landscape, burying everything in their path. The surrounding basins would have filled with searing ignimbrite flows, pyroclastic surges so hot and fast they travelled at highway speeds, vaporising forests and boiling lakes. These flows welded into dense glassy rock that we now see preserved as intracaldera quartz ignimbrite, found interlaid with bedded rhyolite breccias inside the old volcanic basin. The eruption likely lasted days to weeks, cycling through phases of column collapse, fountain-fed flows, and caldera collapse. Each phase would have emptied more of the magma chamber, causing the land above to sink further and further. A volcanic winter inevitably followed the eruption. When a magma chamber that size is partially drained, the crust above it can't support its own weight. It collapses, sometimes gradually, sometimes catastrophically, along ring faults that encircle the chamber like the edges of a giant piston. That's exactly what happened at Mungore. As the eruption raged, sections of the crust sagged inward by hundreds of metres, then kilometres, producing a vast collapsed cauldron, a 50 to 35 kilometre ovoid depression orientated east to west, cutting across the region's older north to northwest structural grain. The fault-bounded margins of the caldera were marked by ringdites of porphyritic biotite granite and rhyolite, some up to 200 metres thick, intruded along the collapsing edges like molten stitches holding the wound together. In the aftermath, the centre of the caldera was a wasteland, a steaming ash-filled depression kilometres deep, ringed by shattered fault scarps and domes of still cooling lava. Inside that depression, enormous quantities of hot ash and pumice continued to pour in, accumulating to thicknesses of perhaps a kilometre or more. These layers welded into the massive intracaldera ignimbrite sequences we see today, sometimes intruded by younger granites that represent the lingering heat of the system. After the main eruption ceased, the magma chamber didn't go cold right away. It refilled, partially, with new magma, a process known as resurgence. The floor of the caldera began to dome upward again as molten granite pushed its way back into the base of the depression. This produced a body of weakly porphyritic biotite granite, texturally homogeneous and chemically similar to the rhyolites that erupted earlier. Geologists interpret this as a resurgent pluton, the frozen heart of the volcano as it tried, unsuccessfully, to come back to life. And this pluton is actually visible when using gravity images. You can see two domes where magma attempted to reach the surface. It's little things like this that really leave me awestruck and that remind me of why I'm so fascinated by geology. We get to not only peer beneath the surface and see the caldera's shape, but the places where, post-eruption, this caldera struggled to stay alive before finally giving in to its demise. So by this stage, the supervolcano was effectively dead. The eruptions had spent their fury, the remaining magma congealed, and the once towering volcano collapsed into itself. Rain and wind began the slow, patient work of erosion, carving valleys through the tuff and granite. Within a few million years, vegetation returned, life crept back across the scar, and the caldera faded into geological memory. It turns out that the Mungore supervolcano didn't just leave behind ash and granite, it also left behind metal. Today, more than 200 million years after the eruption, geologists and exploration companies are combing the same hills, searching for traces of gold, silver, copper and molybdenum. ActiveX Limited, one of the companies working in the region, holds permit rights over the old caldera margin, where the ancient Perry Fault Zone cuts through the volcanic and granitic rocks. That fault, the same one that helped Mungore's magma reach the surface in the first place, still marks zones where mineral-rich fluids once surged upward through the fractured crust. Those fluids cooled, crystallizing veins of quartz laced with metals. What survives today is subtle, but to the trained eye, unmistakable. The Mungore complex forms a broad, elliptical zone of granites, rhyolites and ignimbrites, their textures and chemistries revealing the fingerprints of that ancient cataclysm. The region also preserves a second volcanic structure immediately adjacent to Mungore, a cluster of rhyolite domes and a broad regional sag. Some researchers believe this may represent a second caldera, formed by a companion eruption in the same magmatic system. Together, the pair mark a volcanic province of staggering proportions, a field of rhyolite and granite that once must have rivaled the volcanic plateaus of New Zealand and Western North America. The irony of Mungore is that, unlike Yellowstone or Taupo, it's been so thoroughly eroded and buried that it almost escaped unnoticed. There are no dramatic cliffs or giant caldera lakes to portray its existence. For decades, it was simply mapped as a granitic complex. Only with detailed geochemical and structural work in the 1990s did geologists realise they were looking at the remains of a collapsed caldera system, and not a small one. So, in every way that matters, size, structure and eruptive sequence, Mungore fits the template of a VEI-8 supervolcano, the largest volcanic eruptions known to exist. But because the deposits are deeply eroded, and no direct ignimbrite volume has been measured, geologists still refer to its eruptive output as unquantified. Even so, by comparing it to similar sized calderas, a reasonable estimate of 1,000 to 2,000 cubic kilometres of eruptive material fits perfectly, enough to blanket half of eastern Australia under metres of ash. Because of this, it's difficult to escape the conclusion that Mungore was a global-scale volcanic event. Today, if you walk along the old quarries and road cuttings near Gayndah or Mount Perry, you can still find the relics. Welded ignimbrite with flattened pumice fragments, rhyolitic breccias with shards of volcanic glass, and granites that once crystallised kilometres below the surface of the eruption. Every mineral grain, quartz, feldspar, biotite, tells part of the tale. So next time you hear about Yellowstone's restless magma or Taupor's explosive past, remember that Australia has its own giants. They're just older, quieter, and hidden beneath the dust of time. I hope you found this as interesting as I did. And as always, thanks for watching. A billion years ago, in what is now the heart of Australia, there was a supervolcano so immense that it dwarfs anything alive today. Known as the Talbot Sub-Basin, this prehistoric volcano unleashed eruptions with volumes exceeding 1,800 cubic kilometres of molten rock in a single blast, enough to bury an entire modern city beneath kilometres of ash and volcanic glass. It erupted repeatedly for over 30 million years, each time creating new overlapping calderas in a cycle of destruction and renewal. When it was alive, it spanned nearly 50 kilometres across, blasting material deep into the sky with an intensity that would have rivaled or surpassed Yellowstone, Taupor or Toba. Unlike Yellowstone, its VEI 7 to 8 eruptions were fed not by a mantle plume, but by the slow cooking of a continent's crust, a supervolcano without a hotspot, operating in the thinning heart of a continent that was still coming together. This was no ordinary eruption centre. The Talbot volcano was part of a vast bimodal volcanic system, basalt from the mantle below and silica-rich rhyolite from the melting of the crust above. Its rhyolites are chemically unique, depleted in heavy oxygen isotopes, marking them as products of intense interaction between magma and surface water at astonishingly shallow depths. Over time, these eruptions built a volcanic pile up to 9 kilometres thick, and left behind what is now the largest accumulation of low delta 18O rhyolite on Earth. What remains is the eroded skeleton of a super-eruption province, an ancient furnace that forged new crust and helped shape the very foundations of Australia. Today, if you stand on the dusty plains near the borders of Western Australia, South Australia, and the Northern Territory, there's little to give away the violence that once raged here. The desert is quiet, its mesas low and sunbaked, and the wind drags across quartz pebbles and dry salt pans. But hidden beneath your feet lies the scar of that colossal engine. The long frozen remains of magma chambers and caldera walls that, a billion years ago, would have plunged the world into volcanic winter. Back in the Mesoproterozoic era, around 1.08 billion years ago, Australia as we know did not exist. The land was a patchwork of drifting continental blocks slowly colliding and welding together into the supercontinent Rodinia. Between these growing masses lay zones of weakness, regions of thin crust where heat from the mantle could seep upward. One such region was the Musgrave Province, trapped between the North Australian and South Australian cratons, two of the most ancient fragments of Earth's crust. For hundreds of millions of years before the Talbot eruptions, the Musgrave Province had been under extreme thermal stress. Earlier tectonic collisions, especially the Musgrave orogeny around 1.2 billion years ago, had crumpled, stretched and baked the crust, charging it with enormous amounts of residual heat. The rocks were already simmering at near melting temperatures when fresh magma began to intrude from below during what geologists call the Giles event. That combination, a thin fractured crust and a deep source of magma, was the perfect recipe for catastrophe. When basaltic magma surged upward from the mantle, it stalled in the crust and began melting the rocks around it, generating huge chambers of A-type rhyolite, a dry, iron-rich, silica-heavy magma known for its explosive temperament. Over thousands of years, these chambers ballooned in size, storing more and more pressure until the crust above finally fractured and collapsed. The result was not a cone like Mount Fuji or Mount St. Helens, but a caldera tens of kilometres across, A volcanic depression formed when the ground itself caved in after being emptied of magma. Normally, when identifying supervolcanoes, the caldera can be clearly outlined using magnetic or gravity data, but that isn't the case with the Talbot system. The subsurface maps are cluttered with overlapping magnetic signals from later intrusions, mafic sheets, and structural reworking, making it difficult to distinguish any single caldera rim. To complicate matters further, Talbot wasn't just one volcano, but a cluster of overlapping piggyback calderas formed over tens of millions of years. Each new eruption reshaped the previous collapsed structure, blurring its boundaries. After the eruptions ended, the entire region experienced significant post-caldera deformation and erosion, further distorting or burying the original ring faults. As a result, the caldera outline has become obscured beneath a patchwork of later geological processes, leaving only faint traces of what was once a vast supervolcanic complex. But with that being said, if I was to take an educated guess regarding where the eruptive centre was, based on faults, geological layers and magnetic anomalies, I'd say it was here. And this fits quite neatly with a map posted in the study, The Mesoproterozoic Thermal Evolution of the Musgrave Province in Central Australia, Plume versus the Geological Record. In this image we can see that the Mungore shear zone cuts right through the caldera location. When viewing the caldera under magnetics and gravity, there appears to be a linear feature cutting into the circular shape. This linear feature is almost certainly the Mungore shear zone. On geological maps, there are some ring-like faults that also add weight to the assumption that this was more or less the explosive centre of the numerous super eruptions that make up the Talbot Sub-Basin. The first of these cataclysmic eruptions produced a rhyolite deposit estimated at nearly 1800 cubic kilometres, comparable to and greater than the largest eruptions known on Earth. Imagine the ground splitting open and a column of incandescent ash shooting 40 kilometres into the stratosphere. The column collapses under its own weight, sending pyroclastic flows, clouds of gas and molten glass, racing across the land faster than any storm. For hundreds of kilometres, the landscape is buried beneath searing ash flows hundreds of metres thick. Rivers vanish, mountains are levelled, and the sky turns dark for months or years. When the eruption finally ceases, the crust above the emptied magma chamber collapses inward, forming a depression 40 to 50 kilometres wide. Then, over time, a new magma chamber forms beneath it, and the process repeats. Each new eruption occurs within the footprint of the last, creating a piggyback sequence of calderas stacked atop one another, a geological nesting doll of destruction. This cycle repeated many times over the course of 30 million years, leaving behind layer upon layer of welded ignimbrite and flow-banded lava that together form the Talbot Sub-Basin. The cumulative volume of rhyolite erupted during this era reached several thousand cubic kilometres, rivaling the greatest volcanic provinces in history. What happened at Talbot wasn't a single event, it was a long-lived volcanic field of super eruptions, a slow-motion cataclysm that fundamentally reshaped Central Australia. One of the most extraordinary aspects of Talbot's rocks is their oxygen isotope signature. Every sample of rhyolite and zircon from the sub-basin shows unusually low delta-18 oxygen values, so low that they can only be explained if the magma had mixed with water that once existed on the surface. This means that before each eruption, enormous volumes of groundwater or rainwater must have infiltrated the crust, circulating through hot rock and altering its chemistry. When new magma intruded into these waterlogged zones, it absorbed that isotopic signature, creating low delta-18 oxygen rhyolite. This is incredibly rare in the geological record. The only comparable system on Earth today is the Snake River Plain in the Yellowstone Plateau, which also produces oxygen-depleted rhyolites, but these eruptions are much younger, only a few million years old. The Talbot system is over 1 billion years older and yet displays the same isotopic fingerprint, suggesting the same processes were at work in the deep past. Shallow crustal magma chambers repeatedly remelting their own volcanic roofs under a continuous flush of meteoric water. This isotopic depletion tells us something profound about the structure of the volcano. The chambers that fed Talbot's eruptions must have sat within the upper 10 kilometres of the crust, where surface water could still circulate. That's astonishing for an eruption field of this magnitude, because it means the magma's accumulated at very shallow depth, storing colossal energy just below the surface before blowing it sky high. Most modern supervolcanoes are linked to mantle plumes, those deep columns of hot rock that rise from the Earth's core mantle boundary, but the Talbot supervolcano was different. It wasn't fed by a plume at all. Its heat came from the crust itself. After hundreds of millions of years of compression and radioactive decay, the crust of the Musgrave province was already hot enough to melt under only modest additional heating. When fresh mafic magma from the Giles event intruded into this firmly primed crust, it triggered runaway melting. The result was a colossal volume of juvenile felsic magma, new crustal material rather than recycled continental rock. Talbot therefore represents not just a destructive event, but a creative one. It generated new continental crust on a massive scale, helping to thicken and stabilise the interior of Australia. This makes the Talbot Sub-Basin a geologic paradox, a system that behaved like a plume-fed hotspot but was entirely self-generated, powered by crustal heat and local tectonics. It shows that you don't need a plume to make a supervolcano. Sometimes all you need is a thin piece of lithosphere, a trapped pocket of juvenile magma, and a lot of time. As each eruption cycle ended, the collapsed caldera filled with welded tuffs, lava domes and granophyric intrusions, the solidified remains of magma chambers. New basalt flow sometimes poured into the basin, marking a return to mafic volcanism before the next rhyolitic phase began. The landscape alternated between violent eruption and long dormancy, slowly building a volcanic succession up to 9 kilometres thick. Over time, as the crust stabilised, the final magma chambers cooled and crystallised into granite. The last eruptions likely produced sluggish domes rather than explosive ash clouds, signalling the gradual death of the volcanic field. Eventually the system fell silent, buried beneath younger sediments and eroded by a billion years of weathering. In total, the Talbot Sub-Basin likely produced many thousands of cubic kilometres of rhyolite, easily ranking it among the greatest volcanic accumulations in Earth's history. But unlike Yellowstone, which remains restless today, Talbot's fire has been cold for more than a billion years. Its heat has long since faded, leaving behind only isotopic clues and frozen magma bodies deep in the crust. Because the evidence is so ancient and subtle, understanding Talbot has taken decades of detective work. The breakthrough came in the early 2010s, when researchers from the Geological Survey of Western Australia, notably David Smithies and colleagues, combined geochemical data, zircon isotope studies, and regional mapping to reveal the true scale of the system. The results stunned even seasoned geologists. Not only was Talbot among the largest ancient volcanic provinces ever found, but its rocks recorded the same kind of isotopic fingerprints seen in young supervolcanoes, making it the oldest known analogue of Yellowstone on Earth. They coined the term piggyback supervolcanoes to describe its sequential calderas and proposed that the Talbot field represents a new category of plume-free supervolcanism, driven entirely by crustal processes. In doing so, they redefined how scientists think about the origin of giant eruptions, showing that the Earth's crust, under the right conditions, can generate its own cataclysm without help from the deep mantle. Today, the Talbot Sub-Basin sits in silence beneath the Australian desert. Its rhyolite domes have eroded into low hills, its caldera rims softened by a billion years of wind. No one lives there and few people ever visit, yet it remains one of the most extraordinary geological sites on the planet. A frozen memory of a time when the continent itself was molten and alive. I hope you found this as interesting as I did, and as always, thanks for watching. If I told you that one of Australia's largest volcanic eruptions, maybe among the largest known in the entire country, happened just northeast of Melbourne, you'd probably think I was joking. But tucked beneath the forests around Marysville, Lake Mountain and the Rubicon Valley lies a hidden giant, the Cerberean supervolcano, a Devonian monster with a collapsed volcanic crater or caldera that spans about 27 kilometres across. Inside that ring, researchers have identified around 900 cubic kilometres of ignimbrite, volcanic ash and pumice welded together into rock just inside the collapsed caldera. Let that sink in. 900 cubic kilometres is enough to bury the entire Greater Melbourne region under a layer of superheated volcanic ash hundreds of metres thick. And that's only the material preserved inside the crater. The total eruption volume, including material blown far across the ancient landscape, was almost certainly much larger. This thing was a supervolcano, make no mistake. A full-scale caldera-forming eruption capable of collapsing a huge section of the crust into an emptied magma chamber and blanketing vast areas of eastern Australia in glowing clouds of pyroclastic fury. And speaking of magma chambers, this wasn't some little pocket of molten rock hiding under a fault line. The Cerberean supervolcano sat on top of a batholith-scale magma system, built from multiple batches of magma rising and accumulating over millions of years. It was enormous, chemically diverse and incredibly hot. Upwards of 875 to 940 degrees Celsius for the uppermost rhyolitic melts, and still at least 780 degrees Celsius for the lower ones. So how did such a monster come to exist here? Why central Victoria? Why then? And how does a volcano grow large enough to literally swallow a piece of the continent as it collapses in on itself? To answer that, we need to peel back the layers of geological time, zoom way out to the scale of continents, and set the stage for one of the most explosive chapters in Australia's deep time story. Long before Victoria ever shook with the fury of the Cerberean supereruption, the land beneath it was already extraordinary. Central Victoria sits above a block of ancient crust known as the Salween Block, which is itself part of a much larger fragment called Van Dieland. You can think of Van Dieland as essentially Tasmania before Tasmania existed, an exotic microcontinent composed of Proterozoic and early Paleozoic rocks that once drifted independently along the edge of Gondwana. Geological evidence suggests that Van Dieland, including what we now call Western Tasmania, collided with the margin of eastern Australia sometime around the late Ordovician to early Silurian, generally placed between 440 and 430 million years ago. When it welded onto the Gondwanan edge, it fundamentally changed the crust beneath what would later become Victoria. Instead of simple continental crust, Central Victoria inherited a layered, chaotic, incredibly heterogeneous block of deeply metamorphosed greywackies, volcaniclastic sediments, and rift-related volcanic rocks. This exotic basement block mattered immensely because it became the raw material for the Cerberean supervolcano. Deep beneath Central Victoria, the crust was riddled with ancient sediments that, when heated to sufficiently high temperatures, produced exactly the kind of magma needed for enormous explosive eruptions. These were S-type magmas, formed by melting sedimentary rocks rather than igneous ones. S-type magmas tend to be sticky, silica-rich, water-rich, and dangerously volatile. They are the sort of magmas that erupt as giant pyroclastic flows, rather than as calm, flowing lava. By the Devonian, Central Victoria had been through hundreds of millions of years of tectonic chaos. Subduction zones had opened and closed. Volcanic arcs had come and gone. This constant tectonic switching created faults, fractures, and weaknesses throughout the crust. But more importantly, it thickened the crust and trapped heat. Thick crust behaves like a giant slow cooker, particularly when new hot magma from the mantle keeps intruding from below, and intrude it did. Instead of one enormous, uniform pulse of basaltic magma rising into the crust, the Salween Block was repeatedly injected by many thinner sills and sheets of mafic magma. These small intrusions behaved like a long series of blowtorches heating the basement rocks. Each intrusion roasted the local crust, melted part of it, and allowed tiny pockets of granitic magma to form. Over millions of years, these pockets migrated upward, merged, mingled, and slowly grew into massive bodies of melt. The important thing here is that the crust was not melted evenly. Because Van Dieland was a patchwork of different sediments and volcanic rocks, each region of melting produced magma with a slightly different composition. Some areas melted greywacke more completely, others melted mudstone, and others melted volcaniclastic rocks rich in iron and magnesium. This is why the Cerberean eruptive units, the Rubicon ignimbrite, its high and low aluminium variations, and the Lake Mountain ignimbrite are chemically distinct from one another. They were not born from the same melt, but from different pockets of crust that melted together at different times. By the time these pockets had risen into a single, larger chamber, the magma body had become a marbled mixture of slightly different magma batches. This heterogeneity is one of the signature features of supervolcano systems. As the magma chamber beneath Central Victoria grew, a huge dome of hot, ductile crust began to balloon upward. The pressure inside the magma chamber increased. Water dissolved in the melt built up. Temperatures remained brutally high. The magma became saturated with volatiles, water vapour, carbon dioxide, and other gases that dramatically increased the explosiveness of silicic magmas. The stage was set for a cataclysm. The eruption likely began with a deep failure in the magma chamber. Perhaps a fresh injection of hotter magma from below destabilised the chamber roof. Perhaps pressure built up along a pre-existing weakness. Whatever the trigger, the chamber ruptured violently. A point explosion sent shockwaves through the crust. Ring fractures propagated outward in a near-perfect circle, 30 kilometres across, slicing the crust with terrifying speed. These fractures opened pathways for magma to rush to the surface. The first pulses of magma erupted explosively, forming towering eruption columns. The high aluminium Rubicon ignimbrite came first, filling the early Caldera basin with pyroclastic deposits. As the eruption intensified, the magma feeding the vent changed slightly, reflecting the transition from one batch of melt to another. The low aluminium Rubicon ignimbrite followed, even larger and more voluminous than the first. The eruption drove pyroclastic density currents, avalanches of incandescent ash, pumice, and gas, outward at hurricane-like speeds. These flows consumed everything in their path, flattening the Devonian landscape and leaving behind a smothering blanket of hot volcanic debris. As the eruption continued, the composition of the magma shifted again. indicating that deeper, slightly more mafic parts of the chamber were now being tapped. This transition gave rise to the Lake Mountain ignimbrite, a rhyodicitic unit representing the final and most voluminous phase of the eruption. The Lake Mountain ignimbrite would eventually make up the bulk of the 900 cubic kilometres of material preserved inside the caldera. But the most dramatic part of the whole sequence was the collapse. As the magma chamber emptied, the roof above it lost support. The central block of crust, kilometres thick, began to slump and sink into the void. This sinking was not gentle, it was catastrophic. The ground collapsed along the ring fractures in a cauldron-style subsidence event, dragging the surface downwards like the lid of a pot falling into boiling soup. The collapse, in turn, triggered more magmas to erupt. The eruption fed the collapse, and the collapse fed the eruption. The result was a vast caldera, rimmed by ring faults and filled with a sea of ignimbrite. If you could travel back in time, you would see fountains of ash darkening the sky, pyroclastic flows racing across a barren wasteland, and the earth literally caving in upon itself. The Cerberean eruption would have been one of the most violent geological events ever to take place on Australian soil, and even though hundreds of millions of years have passed, the ghost of that catastrophe is still visible today. If you open a satellite map and zoom in on the region between Marysville, Lake Mountain, Camberville and the Rubicon Valley, you can trace the faint but unmistakable curve of the caldera rim. The landscape forms a subtle, giant circle, its arc picked out by ridgelines, valley orientations, and a distribution of volcanic rocks. It's not obvious to the untrained eye, but once you know what you're looking for, the 27-kilometre wide outline snaps into focus like a fingerprint from deep time. The caldera is still there, quiet, forested, eroded, but undeniably present, etched into the high country like the scar of a wound the earth inflicted upon itself. When the eruption finally ended, the caldera remained active for some time. Magma continued to intrude beneath it, but instead of exploding at the surface, it cooled slowly underground. These late-stage intrusions crystallised into granodiorite, forming many of the granite outcrops now seen in the Marysville region. Over the next several million years, erosion, uplift, folding and sedimentation slowly obscured the caldera. Forests grew, rivers carved through the ignimbrites, the violent past sank beneath a peaceful landscape. Yet the evidence remains. Lake Mountain owes part of its topography to the thick accumulations of ignimbrite. Boulders and cuttings along roads between Marysville and the high country expose welded tuffs, glassy volcanic rocks, and granodiorites that once pulsed with heat. The Rubicon Valley preserves relics of pyroclastic flows that were once hundreds of degrees hot. What makes Cerberean so fascinating is its context. This was not a one-off oddity. During the late Devonian, central Victoria experienced widespread magmatism. Calderas erupted across the region, from Mount Macedon to the Dandenong Ranges to other areas. The crust was extraordinarily fertile for melt generation. The Selwyn block supplied sedimentary source material ready to melt. Continuous injections of mafic magma kept temperatures high. Faulting and extension provided pathways for magma ascent. This was the perfect storm for giant silicic eruptions. Cerberean was simply the biggest expression of this magmatic province. The presence of Van Dieland beneath Victoria was crucial. Without that exotic fragment of thickened, heterogeneous crust, the region would not have had the chemical richness required to feed such massive magma chambers. Tasmania's ancient rocks provided the fuel. When Van Dieland welded onto the mainland around 430 million years ago, it carried with it a geological legacy that would one day erupt in spectacular fashion. Today, the landscape above the Cerberean Caldera is quiet and peaceful. Alpine ash forests cover the slopes. Hikers walk trails that follow ancient fault lines without even knowing it. Beneath their feet lies the memory of a supervolcano, preserved in silent stone. The region looks serene, but the rocks tell a different story. They tell of a time when the ground trembled, when the earth roared, when the sky filled with darkness, and when an entire piece of crust collapsed into a sea of magma. This eruption undoubtedly caused a volcanic winter as well. But understanding Cerberean is not just about studying an ancient eruption. It's about recognising that Australia, often seen as a geologically quiet continent, has a deep time history every bit as dramatic as Yellowstone or Toba or Topor. The Cerberean supervolcano is one of the greatest geological stories on the continent, hidden, forgotten, but vast in scale and astonishing in power. If you walk the forests of Marysville and Lake Mountain with that in mind, the land suddenly feels different. Every granite boulder becomes a remnant of a cooling magma chamber. Every roadside cutting becomes a window into an inferno that once raged with unimaginable force. And the tranquility of the landscape becomes even more remarkable when you realise that beneath the trees lies the shattered heart of a supervolcano. I hope you found this as interesting as I did. And as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.